halfway controlled rectifier with RL load. Okay. So yesterday what we have seen? Halfway controlled rectifier with today we are going to see RL load. Now we know the basics of the circuit diagram for half-wave rectifier. That is, first we will be having the transformer for giving AC as the input. Okay. So our input is the AC supply of 50 Hz. Next to the transformer, we will be having what type of switch we are using?
Tiles.
We are using tiles. So here the load is both the resistive as well as the inductive load. So can you say some example for resistive and inductive load? Since it is thyristor, we will be having three terminals: anode, cathode and gate. Okay. And now this is resistive load and this is inductive load. First, what is resistive load? We have seen halfway control rectifier with resistive load means, the resistive load means it can be a any of our resistive load means we have taken a bulb lamp. Okay, so that is also what? It is observing some value of current. Okay, and it is functioning. Okay, in terms of inductive load means it should have the capacity to store the energy. Okay, so inductance will store what? Inductance will store. What about inductance and what about capacitance?
Capacitance store a charge.
Which means current. Okay, and inductance will
Store power.
power. What does that mean, power? Voltage. Okay, and so now RL circuit. Okay, so what will be the working principle? Whatever I am giving an AC supply, the transformer will give the voltage. The voltage should be, or the voltage should not be
More than
greater than the, what I have told you yesterday, important point. Whatever input voltage I am giving, it should not be greater than the forward or reverse blocking rating of the thyristor. Okay, so whatever the voltage input as we are giving, it should not be greater than the forward and the reverse blocking current of or blocking value of the ratings of the thyristor. It should withstand that current and voltage. Okay, from the input. Okay, so after giving, it will be in the anode to cathode, which means it is in the forward bias condition and it reaches to the load, that is RL load. Okay, we are using resistive RL load, resistive inductive load. Okay, and now after writing the working principle, what sort of input we are giving? We are giving a sinusoidal. Okay, what is the nature of the inductance? So this is our input voltage with respect to time. In terms of AC, so we are in omega t, that is with respect to angle of frequency and time. Okay, so after that, so when it will the thyristor will turn on? Whenever we are giving a positive voltage supply, what will happen? After giving the firing angle, okay, so once the gates I already told you the SCR, whenever when it turns on with respect to the gates signal, or we can say that as pulses, or we will be saying it as firing angle, and that is denoted as the alpha. So after some degree of alpha, this is your firing angle alpha. Okay, so since it is halfway, only it will conduct in the during the positive half cycle. forward as well as in the reverse, that is in the positive half cycle as well as in the negative half cycle. Now we are seeing half wave rectifier. So it will connect only during the positive half cycle, since there is only one forward bias for a one circle, that is SCR. Okay, and now I have given the firing angle with respect to the time omega t. Okay, so once the firing angle is triggered, we will say it as when the SCR is triggered, which means the SCR is turned on now. Okay, so what will happen till that? There will be no flow of current. After that, what will happen? I am taking the response for output voltage with respect to time, and likewise output current with respect to time, and likewise thyristors voltage with respect to time. Okay, first now output voltage, still alpha, before giving the gate pulse to the thyristor, it won't turn on. Okay, so once it turns on, what is the output voltage we will be receiving at our load side? Okay, so that is during alpha our voltage will get increases, and it will comes to rest position at the pi, 0 pi, and the second cycle is 2 pi. Okay, so it will reach 0 to the pi. It maintains at 0 till the next triggering starts. Okay, so next is triggering is starting over. So I have drawn it wrong, right? Wait. So firing pulse we are using here, right? Here only we are giving firing pulse. Okay, so once the firing pulse is given over here, it will not turn on. Okay, on the next 3 pi, it will reach us again to the 0. Clear now? Okay, now so once the firing pulse is given, it will turn on at the same point, and it is 0 at the first half cycle pi, and it will be 0 till the next triggering pulse alpha is given to the SCR. So next cycle it will, the voltage will increases and decreases accordingly. After that, what is the current? Then here the load is inductive in nature. So in inductive nature it will store some sort of current. Okay, so what it will do?
Reduce the
Same here, it will be zeroed initially, since the load is inductive. Okay, since the load is inductive, it will store some current. Okay, since it is storing some current, initially as like the resistive load, in resistive load we have seen like this, right? The current also in phase to the voltage. This is the response we have seen for the resistive load, right? Like how the voltage increases initially and it is gradually decreases at the final pi stage. Here in resistive load, the inductance is what doing? It is storing the current. So initially it won't increase as like the voltage. It will start to increase gradually. Okay, it will start to increase gradually after storing after some time it will reach its maximum value. Later on it will decreases to 0. Okay, after that what happens? Still it is having some charges. Even though the SCRS, now what happens? Even though it is turned off, even though the voltage is 0 now, due to the stored current in the inductance, it won't be 0. During the reverse bias of the SCR also, it will conduct. Okay, during the reverse bias also what? It will conduct. This is the only variation for the RL load. Okay, what you have to say means, due to the inductance nature, the current will not increases at the initial stage. Okay, because it is storing some amount of energy. The inductive nature is that only. Okay, so the current is gradually increases, and after reaching a maximum peak value of current with respect to some time, what happens? It is decreasing, and after reaching the 0, even though the voltage is 0 over here, due to the stored current, it will conduct. Okay, the current will still flowing during the reverse bias of the SCR. What is this half cycle? This half cycle is the reverse bias condition, right? So during the What is this angle that? Due to the stored current, still there is a flow of current, right? That particular angle is taken as beta. Okay, so it should be taken as beta. So for the current or from the voltage, from where it is where till where it is conducting?
0 to
From 0 to here it is
pi.
pi. Okay, so here it is alpha for current where it is still conducting alpha to beta. So it is conducting is taken from alpha to beta. Okay, so likewise now what is for the voltage across the thyristor? During the voltage across the thyristor, it's straight opposite to the output voltage. Okay, so that is here. If it is 0 means here it will be still in the conduction. Here the thyristor from the alpha towards the next beta. Okay, from the alpha to the beta there won't be any voltage across the thyristors, and after that where it is 0 it will still in the
Beta.
conduction state. Once it will become it will reach to 0. This is the thyristor's conducting state. Okay, so the inverse of it. So when we are seeing it, it will be like this. Okay, so this will continue. That is the voltage across the thyristor. Are you clear up to this? Now you have to derive the output voltage, like the average output voltage. That is V naught. That is equal to, or we can say that what is the output here? This is a rectifier circuit, so it will be converting AC into DC. So what is VDC here? What is the input voltage here? Since it is AC, Vm, that is Vmax, sinusoidal in nature, angular frequency with respect to time. Okay, so VDC is equal to Vm by, we are seeing up to 2 pi, one cycle. Okay, both positive as well as negative. So 1 by 2 pi Vmax, Vm sin omega t. Okay, so now VDC will become 1 by 2 pi integral of where the conduction is starting from the alpha to till the beta. So the upper limit is beta, lower limit is alpha. Okay, who is here? Vm sin omega t divided by, so I have already written this 1 by 2 over here. So Vm sin omega t d of omega t. So while I am integrating sign the same as we have done yesterday, that is VDC is equal to 1 Vm, shall we take Vm is constant, right? So Vm is constant, we have taken that out of integral. So Vm by 2 pi, if I integrate sin, it will become minus cos omega t, the limit ranges from alpha to beta. So this can be written as Vm by 2 pi, upper limit minus lower limit. So it is minus cos beta, already upper limit minus lower limit, minus of minus cos alpha. Clear up to this? So therefore, what is our VDC then now? VDC is equal to Vm by 2 pi. You can write that as, you write it plus cos alpha first.
Cos alpha minus cos beta.
Cos alpha minus cos beta. This is the voltage, output voltage. Okay. Then what is the output current? IDC is equal to I equal to VDC by R. Here we are not only seeing for the resistive load. In first half the rectifier we have seen resistive load. It is Vm by R. Now for inductive load what it is? R L. We should will be writing the like that. For RL circuit, so for circuit networks, I will be writing for RL. The load. No, it is not R by. R plus that is in terms of omega, or we can say in terms XL.
Yes, yes.
Okay. So it will become into cos alpha minus cos beta. So you can find out the power delivered also. VDC is equal to VDC into power P is equal to V into I. So VDC is equal to VDC into IDC. Multiply the both. Okay. Let us VDC. Here VDC by M means we have to just substitute that. What is that VDC?
VDC
VM
VM by 2
pi.
cos
So when we multiply it will become Vm square divided by 4 pi square into R plus omega into cos alpha minus cos beta the whole square. That is the power delivered by the half-wave control rectifier with RL load. Okay. So there is a mistake. It is not omega n. It is XL, inductive reactance. Okay. While saying it, I am saying XL. While writing it. So now, in the same circuit, okay, to increase the reliability of the circuit. Okay. So what is the purpose of here this inductance? It is storing some sort of current. Okay. So during reverse bias of the SCR also, the conduction is still there. Okay. So to make it more reliable, we are going for a diode. So this is R load with the diode is said to be freewheeling diode. Okay. So we are going for a diode that is going to be connected parallel to the load. We have taken the diode as diode. For what? Why we are going for this diode means since the inductance is storing some sort of energy. Okay. During when the SCR is acting as the reverse bias condition also, the stored energy can flow through the diode towards the load. So this nature is will increase the reliability of the circuit even more. So for that purpose, we can add a diode which is parallel to the load. The diode is said to be what? Freewheeling diode. Okay. The same circuit diagram. One more small topic with freewheeling diode. Just to add a diode parallel to the load. What is the purpose for it? What is the purpose of it? To increase the reliability of the circuit.